Alright, we're going to start on types of random variables. We're going to look at first. Alright, and the first type of random variable we're going to look at is a discrete random variable. Alright, a discrete random variable is a random variable which has a countable number of possible outcomes. So, if you can count the number of outcomes, it's not like an unlimited number of outcomes where, you know, if I want to know the probability that of someone, you know, that if I randomly selected a female, what is their height? Well, it's not like that we would have an unlimited number of outcomes, but if we got really specific with the measurements, like down to the nanometer, then there'd be just so many different types of outcomes that I really wouldn't count that as a discrete random variable. But if it's something where, like rolling a die, how you know you're going to have 6 different outcomes, then that would be a discrete random variable. So, for example, let's say that I let x be the variable. Well, what are my outcomes if I roll one die, one 6-sided die? I'm going to get a 1, a 2, a 3, a 4, a 5, or a 6. So it has a countable number of outcomes. And I could also list all of those probabilities if I wanted to. So the probability of each one of these, so the probability of rolling a 1 is 1 out of 6. A 2, 1 out of 6. Same thing for every one of them, 1 out of 6. Okay, so notice I have a countable number of outcomes. Also notice, what do I get if I add up all of the probabilities? What's the sum of the probabilities? Yeah, it's equal to 6 over 6, or just 1. Okay. So there's not, I can't roll a 7, I can't roll a 0. When I roll a die, I'm going to get one of those 6 numbers. Alright, so me drawing that table, that's called a probability distribution. I mean, you can draw it ever how you want, but this right here, me drawing this table, that's called a probability distribution. Now, so that's what a discrete random variable is. A continuous random variable that's a random variable that can assume any value on a continuous segment of the real number line. So that's the main difference between discrete random variable and continuous random variable, is that a continuous random variable can assume any value on a continuous segment of the real number line. So like, if I knew, I'm just gonna make up something. If I knew that maybe the shortest person in the world was I don't know, let's say 3 feet tall, and the largest person or the tallest person in the world was 8 feet tall, then, we could map out a segment here on the number line from 3 to 8, and I know that everybody's height in the world then would be between 3 feet and 8 feet. Now, is that true? No, I don't know the specifics. But there are an infinite number of possibilities between 3 and 8. Okay, if we were to measure things maybe with a decimal or something like that. So that's the biggest difference. A continuous random variable is a random variable that can assume any value on a continuous segment of a number line. All right, the example that the book gives, it says a local restaurant has an express policy that states that lunch will be served within 15 minutes of ordering, or it will be free. I would go there a lot then. Obviously, the restaurant is keenly interested in not giving away its product and delivering its promise of a timely lunch. But the length of time to prepare each meal varies because the difference in preparation times of each dish, the load on the kitchen, and the experience of the chefs and waitresses. So, look at the next slide. It says, identify the random variable. X is the time between ordering a meal and receiving it. So what kind of answers could we get? It says the range of values from 0 to infinity. All right, maybe they already have the meal made and they just, that never happens really. I guess unless you go somewhere that has pre-made items like a bakery, you're not going to get it when you order it. But I guess they could take forever to make it. Maybe they never get it made. We went into a restaurant the other night. I guess it was last Friday, and it was really packed. And whenever we sat down and we ordered, it took a little while to get our order, but the people beside us had been waiting over an hour, and so they walked out. They were just furious. But sometimes that happens. Things come up. You never know what happens back there in the kitchen. So, so I guess they're still waiting on their meal, right? So they just left. So that would be infinity. And the probability density, it says it's unknown, but could be approximated using historical data. So I'm sure that if they say 15 minutes, the reason why the restaurant's saying 15 minutes is because probably 99% of the time they can prepare the meals in 15 minutes or less. Now, something like, they may have a fire in the back. You never know. Something could happen to throw that off. But it's not very likely. So that's why they settled on 15 minutes. Like I said, there's not a lot to the first section there. That's the main two types of random variables. We'll look at discrete random variables and continuous random variables. So first we're going to focus on discrete random variables. So we have a couple of guidelines for discrete random variables. We know that all those values have to be countable, and we have to know the total number of outcomes. But there are two main properties or characteristics that discrete probability distributions have to have. So if we're talking about discrete random variables, that's something like this up here. We were talking about rolling a die. And I told you what a probability distribution is, just writing all that down, all the information in the table. So a discrete probability distribution has two main characteristics. So characteristics of discrete probability distribution. So first, the sum of all the probabilities must be equal to 1. All right. Second, the probability of any value must be between 0 and 1 inclusively, meaning it can be 0 or it can be 1. So it's, if we do have a table given to us, then we can tell if it's a discrete probability distribution by checking those two things. We sum up all the probabilities, so all the probabilities must equal 1, and then look at all the probabilities. If you see any negative probabilities, we know that can't happen. Or if you see any probabilities greater than 1, that can't happen. Okay, so sometimes on the homework they'll throw some tables down and they'll say, does this represent a discrete probability distribution? And that's the two things that you have to look for. So here is an example, another example of a discrete probability distribution. And this is in the PowerPoints. So you can see for tossing a coin, how many times? Let's see. 3 times. So they listed all the simple events. You don't have to have that in a discrete probability distribution. But if you toss a coin 3 times, the probability of getting heads, either you're going to get 0, you're going to get 1, 2, or 3. And so the easiest way to calculate that or figure that out is by bringing up or writing out the outcomes, the sample space, and then for 0 heads it will be the only one without a head. Well, there's 8 of these, so the probability is 1 out of 8. And then the probability of getting 1 head, there's 3 of those that have 1, so the probability is 3 out of 8. 2 heads, there's 3 of those with 2, it's 3 out of 8. And then 3 heads, there's only 1 possibility, so it's 1 out of 8. If you sum all of those probabilities up, which is what they're doing here, you can see they do get 1. So that is a discrete probability distribution. All right, let's work this next problem. I don't think it's too tough. It's in the PowerPoint as well, but I'll copy it up here. Then we can look through the PowerPoint if we need a little help. All right, so this is talking about a salesperson. Again, this is in your PowerPoint. So this salesperson says, it says they've kept records of computer sales the last 200 days. Okay, so what this means is he sold 0 computers 40 times, 1 computer 20 times, 2 computers 60 times, 3 computers 40 times, and 4 computers 40 times. So it says he recognizes that his daily sales constitute a random process, and he wishes to determine the probability distribution for the daily sales. From the probability distribution, he would like to determine the following: the probability that he will sell at least 2 computers each day, and the probability he will sell at most 2 computers each day. So we have to understand the problem to be able to figure out the probability. It's not too bad. So the probability of at least 2. The probability of at least 2 computers. Another way to write that, if you let the number of computers that he sold in a day be X, then how could I rewrite that? I could say the probability that X at least 2 would be greater than or equal to 2. Alright, so how do I find the probability of X is greater than or equal to 2? Well, I'm going to need to, for greater than or equal to 2, that's the probability that X equals 0, or not 0, X equals 2, plus the probability that X equals 3, plus the probability that X equals 4. Alright, so I need to figure out those 3 probabilities by looking at this frequency distribution. So we're told that we have 200 days. That's how many days that this salesperson kept these records. So the probability that X equals 2, it looks like he sold 2 computers on 60 of those days. So that would be 60 out of 200, or 6 out of 20, or what is that? Is that right? How do I reduce that fraction? 3 out of 10, or 0.3. Okay. Am I just making those numbers up? No, I got them out of the table, right? You need to pay attention. So the probability X equals 3. Let's see. He sold 3 on 40 of those days. So 40 out of 200. So that's going to be 4 out of 20, or 1 out of 5, which is what? 0.2. And then the probability that X equals 4. He sold 4 computers on 40 days. So that's 40 over 200 again, which we just showed was 0.2. So the probability that this salesperson will sell at least 2 computers is going to be equal to 0.3 plus 0.2 plus 0.2, or 0.7. So what does that mean? That means there's a 70% chance that this salesperson will sell at least 2 computers. Oh, part A. Yeah, part A is at least. So now let's do at most. Let's do that one now. So part B was at most. So How could we write that? The probability of at most 2 computers. If we write that using math symbols, where x is the number of computers, what does at most 2 mean? That would be less than or equal to 2, right? At most 2. So that's 2 or 1 or 0. Okay? So that's the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2. All right, we're going to get that information from the table again. So let's look back at the table. So he sold 0 computers 40 times. So that's going to be, let me do that over to the side. So probability that x equals 0 is 40 out of 200, which I've already simplified on one of these others, right? Or 2 of the others. That's 0.2. The probability that x equals 1. So how many days did he sell 1 computer? 20. So that's 20 out of 200. So that's going to be 1/10, right? 0.1. And then we have the probability that the salesperson sold 2 computers. So this is going to be 0.2 plus 0.1 plus 0.3, because he sold 2 30% of the time. So what's that going to be? That's going to be 0.6. So that means 60% of the time the salesperson will sell at most 2 computers. All right, is that tough? Not too bad? Now, if you ever are asked if a table is a probability distribution, then you need to make sure you check for 2 things. Remember, that's the first 2 things we went over. So I know there are some homework problems like that. So we want to check and make sure that all the probabilities add up to be 1, and we want to check and make sure that all the probabilities are between 0 and 1 inclusively. So that means it can be 0 and it can be 1. All right. Another value we're going to look at is expected value. All right. Expected value is, in layman's terms, I'll tell you what it is, but expected value is what you can expect to get out over a long period of time. So it's kind of like the average. On average, this is what's going to happen. Okay? So the official statistics definition, and it's there in your PowerPoint, it says the expected value of the random variable x is the mean of the random variable x. So the expected value of x is the mean of x. And the notation that we use for expected value is a capital E of capital X. That's expected value. All right, and that's going to be the mean. So that equals mu. Remember, mu stands for mean. And the way that we get that is we take the sum of x times p of x. All right, so if I was to give you, so this is the same same information as before. So here's a table, and we are going to calculate the expected value for the number of sales per day for this person. So what we're doing is we're figuring out, on average, how many sales is this salesperson going to make. I would think that would be important, especially if you were running a business. You would want to know about how many sales a salesperson is making, right, on average, because that kind of affects your bottom line. All right, so this is the same data that we just looked at. So we have, a 0.2 is our probability for 0 sales, 0.1 for 1 sale, 0.3 for 2 sales, and so on and so forth. So what we want to do is we want to make another column, x times p of x. Now this is in the PowerPoint, but I want to show you how you would do it if you don't have it given to you. All right. So I'd want to just multiply straight across. So 0 times 0.2, that's 0. 1 times 0.1, that's 0.1. 2 times 0.3, that's 0.6. 3 times 0.2, that's 0.6. And 4 times 0.2, that's 0.8. Okay? Now if we take and sum those up, let's see. So 0, that's going to be 0.7 plus 0.6 is 1.3. 1.3 plus 0.8 is 2.1. So my expected value here, so I would expect that this person is going to sell on average 2.1 computers. Now they can't sell 2.1 computers, but that's about how many sales per day that person's going to make or going to have. Now that was pretty easy to figure out because the numbers worked out nicely. There is a way to figure out this mean. If you have technology, you can just type this in as a list, this in as a list, and then do the one variable statistics, and the mean that you get is the mean. So you do have to type it in. If you have a TI calculator, you can type it in that way and do that. But that's not very hard. Just the sum of x times p of x. Now what's difficult is whenever you don't have all this information and you have to figure some of it out. That can be a little difficult. All right. See if I can find us another problem. Maybe one that's not in the PowerPoint. All right, here's one where we have to compare two sets. All right. All right, so it says, in the long run, which plan has the higher payout? So we have the probabilities of getting each payout, and then we have how much the payout is. So if I want to figure out the expected value, this is the probability here. This is like your x value, your random variable. Okay? So this is x, this is p of x. This is x, this is p of x. So I want to know which one has the higher payout. That's going to be the one with the higher expected value. So I need to figure out x times p of x. Okay. So 19% of the time we're going to lose $35,000. All right, so that's negative 6,650. So I'll just write it right here. X times p of x. So negative 6,650. 21% of the time, or 0.21, we're going to lose $5,000. Alright, so that's negative 1,050. And then 60% of the time we're going to gain $85,000. Alright, so let's find the sum of those. So 43,300. Who knows? Maybe this is, let's just say this was flipping houses, and plan A, maybe we're flipping houses in this certain city, and on average, 19% of the time I lose $35,000 when I flip the house. It's like buying a house, renovating it, selling it. 21% of the time I lose $5,000, but then 60% of the time I gain $85,000. So over the course of time, it says that will be $43,300 for plan A. Now plan B, I need to do the same thing. So the expected value here, that's our expected value. And now I need to figure out the expected value for plan B. Alright, so 61% of the time I'm going to gain 40,000. That's 24,400. 45% of the time I'm going to gain, 11% of the time I'm going to gain 45,000. $4,950, and then 28% of the time I'm going to gain 75,000. All right, so we need to add those together. Let's find the sum. $50,350. All right, again, that's the expected value. So which plan in the long run is going to have the higher payout? It's going to be plan B. Alright. It's not too bad. You just have to find the sum of x times p of x. Alright. Alright, here's an example that's given in your PowerPoint, so we're not going to work through it. I just want to read through it. And I'll put the information up here so you don't have to look directly at your PowerPoint. You can make some notes on it if you want. It says, suppose you're confronted with two investment alternatives that possess uncertain outcomes described by the probability distributions given below in the table. Which option should you choose? Alright, so here are the two options, and it's kind of hard to tell if you just try to eyeball it. You know, I mean, we hate to lose money, right? So you see two chances of losing money here. Only one chance of losing money there. So, I mean, you know, we just want to say B, just guessing, but of course we don't want to guess. If you can figure out the expected value for each one, though, that gives you the average, what you should expect on average out of these two investments. And so if you go through and you calculate the expected value for each one of these, so you can see that for option A the expected value is 900, so that's what you could expect to make out of this over a long period of time, and the expected value for B is 1400. So even though you see two negative values here, and your mind may want you to think, well, I don't want two chances to lose money, it's that you have a better chance to make money and make more money. So over the course of time, this option B would be the best. Okay, because on average it's going to make $1,400. Alright, so what about the standard deviation and variance of a discrete random variable? The formula is actually not too bad. I mean, it's still, of course, it's standard deviation and variance, so it's going to be a little calculation to do if you do it out by hand. But so let's first look at the variance. So the variance of a discrete random variable, the notation is V of x for variance. It's going to be the sum of x minus mu squared times p of x. So you do need mean to calculate this. So you have to find the expected value. Alright, and then we say x minus the expected value, or the mean. So we'll need a column for that. And then we'll need a column for x minus the mean squared. And then x minus the mean squared times the probability. Of course, using technology is going to make that a little faster, because you can put in one column for your x values, one column for your probabilities, and then use the technology, and it will give you the variance. Or most of the time, the calculators will give us the standard deviation. Right? So if I want the variance, then I have to take the square root of the standard deviation. And so let's write down the formula for the standard deviation. Alright, and so it's the same. It's just the square root of that. So it's the square root of the sum x minus mu squared times p of x. Again, if you have a calculator that will do that. I mean, we were looking the other day and I noticed that someone had one of these calculators whenever I was doing the review for the test. And I said, you know, there is a way to put a data set in on these types of calculators. I just don't teach that. You know, I usually don't teach too much of the technology. But all I had to do to figure it out was I typed in TI30X and standard deviation, and a video came up. First video showed me how to put in data values into these calculators. So whether you have a scientific calculator or you have a TI-83 or 84 or something like that, there are ways to put data sets in. So I'm not saying it's always going to be that easy to do so, especially on the scientific calculators. But either way, and Excel works as well, or Google Sheets or something like that. I even figured out how to do it on the Inspire calculators. I definitely don't want anybody to go out and spend $140 on an Inspire calculator, unless you know you're going to be taking more math classes. Then eventually you might get to the point where you can use that in your math classes. But I have some of these in my classroom, and I don't mind if you use these in the classroom. But I want to show you real quick why it's a little easier. I say it's easier. I mean, you still have to type in the values and everything, but let's see. These calculators can do a lot of the stuff you do in calculus. That's why they're so expensive. But you can also hook probes up to these, and you can figure out things like pressure, gas pressure, and all, you know, temperature changes and everything. Like there's a temperature probe that goes with the calculator. It's pretty neat. But they have an option where you can go in and go to a spreadsheet. So this is just like, just like Excel. And then, you can put in values. Oh, well, let's not put the same value. The reason I say that is, I can do simple things with this, like find the, I figured it out the other day. You have to see how it even tells down here which ones that I have there, and then I can go to menu. See, is it menu? maybe it's not menu. So give me just a second. If I go, let me unselect that. Alright. Yeah, so there's the statistics tab, and then statistics calculation, like one variable statistics. In my list, one, and then I can put in, I might have to put in, well, no, it did it for me. Never mind. So this is the one variable statistics from that list. The average is 5.5. The sample standard deviation is 1.29. Population standard deviation, the number of numbers, so on and so forth. And so you can even put in two sets of data and do the same thing. You've got to select some different options. So there's all kinds of statistical tools out there to help you. And as long as you understand how to do it out by hand, I don't mind you using those shortcuts whenever you can. Now, you do need to understand how to do this out by hand, even though it would take a little bit longer. So let me show you what I'm talking about. Let's say that, what did we choose up here? What was the better option? Investment B. Let me show you how to find the variance for investment B and the standard deviation for investment B. Okay, so we first do have to calculate that the mean or the expected value. So here's what they did. They took, this is x minus mu. Remember, the expected value was $1,400. So you're subtracting that each time. Subtracting the expected value every time. Alright, then once you do that, they squared the number. And since these are pretty big numbers, that's going to give you a big number. And then they said it times the probability. Like for this first thing here, you can see they got 3,872,000. I mean, that's a really big number. But they did that for each x value. All these are your x values. Well, all those are x's. Set it times the probabilities. They did all this calculation. They summed it up. There's the variance. So then if you want the standard deviation, what do we have to do? And I put s squared up here. I meant to put s. I'm sorry. Because s squared still means variance, right? But it says sigma squared. Yeah, sigma squared for variance. And it probably just says sigma here then. Let me see. Let me double check the PowerPoint. Yeah, that's a typo in the PowerPoint. So everybody needs to look. If you're looking at the PowerPoint on page 4 of 7.2, it says sigma squared equals the square root of Vx. That's wrong. It would just be sigma. Standard deviation, is it just sigma, the lowercase sigma, or it's just lowercase s? So where it has s squared, where it has sigma squared on the second formula there, that's just a typo. Alright. So if we wanted to find, and let's not put s since we're using population for all this. If we wanted to find the standard deviation, then we would just take the square root of 6,640,000. And I think that they did that in the PowerPoint, and they rounded to one place and got 1757.8. Alright, so while it will take a little time to do the calculations, it's not too bad. It's not, at least it's not like the regression equations. It's not, it's not that bad. But you can still use Excel, or if you need directions on how to use the calculator that you have, most of the time there are like 10 videos on how to do it on YouTube. Now, yeah, I don't like sorting through all those videos either, but if I search for something and I find a video on a website, especially one like YouTube where it'll have the views and all that, you can tell, usually the one that's been viewed the most or has the most thumbs up is the best one. So if you need help with your technology, that's where I would start. And then if you still can't figure it out, I can show you. I can figure it out. I can figure out how to do the stuff on your calculator for you. All right. Now, what we do on the next section, the next section is 7.3. It's a lot easier. This is one of the easier sections that we cover. The discrete uniform distribution. So the thing with the discrete uniform distribution is that all of the distributions, or I'm sorry, all of the probabilities are the same. So the example that I gave you about rolling a 6-sided die, the probability of getting every outcome was the same. It was 1 out of 6. So that's what happens with uniform distributions. Their probabilities are uniform. So the official statistics definition says, it says one of the simplest probability distributions. That's what the discrete uniform distribution is. Each value of the random variable is assigned identical probabilities. There are many situations in which discrete uniform distributions arise. So think about it like flipping a coin. Same probability for getting heads and tails. For the most part, having a child, same probability for having a male or a female. So those types of situations will be the ones where you would have a uniform distribution. Let's look at the example given here, not the one about the dice, because we already kind of know about it. This says, suppose a purchasing agent has just received a pricing and delivery schedule from a new vendor. So a purchasing agent, that would be like somebody that works for the business that does all the purchasing. Accounts manager type deal, I guess. The person that buys all the stuff. So it says they just received pricing delivery schedule from a new vendor. The delivery schedule was quoted as 1 to 4 weeks. The purchasing agent wishes to construct a probability distribution for the time until delivery. So 1 to 4 weeks means 1 week, or 2 weeks, or 3 weeks, or 4 weeks. Okay, so that would be our x values. And so the probability, if it's 1 to 4, and we assume that they're all the same probability, then each is 1/4. All right, so that is a discrete uniform distribution because each of the probabilities is the same. So let me see if I can find a problem that has a little more substance to it than that. Maybe one where I can calculate something. Alright, so this is a big word problem, but I actually think it's a lot easier than all the words. You know, the words make it seem like it may be complex, but it's not very complex at all. A classmate walks into class and states that he has an extra ticket to a festival on Friday night. He asks everyone in the class to put their name on a piece of paper and put it in a basket. He plans to draw from the basket to choose the person who will attend the festival with him. If there are 17 people in the class that night, what is your chance of being chosen to attend the festival? Round your answer to 4 places. So everybody would have the same chance, right? Everybody has the same probability. And what would that be? So what's the probability of winning or going to that festival? So just be 1 out of 17, right? So if we wanted to make that a decimal, we'd say 1 divided by 17. So to 4 places, 0.0588. So uniform probability, or uniform distributions, discrete uniform distributions, are distributions in which all the outcomes are the same. We can still do all the same things though that we were doing in the last section with this section. So we can still find the expected value. And we use the same formulas. We can still find the standard deviation if we want to. We use the same formulas. It's all the same. It's just that these are a lot easier to deal with because all the probabilities are the same. So you don't have to do any kind of, you know, like we had to figure out, say for this right here, you know, it wasn't difficult, but we had to make sure we multiplied right and we summed things up all right. Well, I mean, we had to do the same thing with the uniform distributions, but if I need a column, if I needed x times p of x, expected value, it's not real hard to figure out, you know, because that would be 1/4. This would be 2/4 or 1/2. That would be 3/4. That would be 4/4 or 1. So you sum all those up and you have the mean of that uniform distribution. If we want to find the variance or the standard deviation, we just use the formula for the variance or the standard deviation that we went over in the last section. So even though it takes a little work, you know, to do this, you can still pretty much, once you find the mean, you can say x, which is whatever you have over here, x minus the mean squared in your calculator, and then say times probability and just write that down. Instead of making one column for x minus the mean, making one column for x minus the mean squared, and making one column for the x minus the mean squared times the probability, I would just make one column and do this in your calculator. Okay? And that's going to be it for today.